Okay, we're now in Chapter 11, Section 2, Problem number 3. And we've got retailers of collectible postage stamps often buy their stamps in large quantities by weight at auctions. The prices the retailers are willing to pay depend on how old the postage stamps are. Many collectible postage stamps at auctions are described by the proportions of stamps issued at various periods in the past. Generally, the older stamps, the higher the value. At one particular auction, a lot of collectible stamps is advertised to have the age distribution given in the table provided. Okay, given a distribution, so we're looking at a distribution here. So this is going to be probably testing the fit of a distribution, looking at the data versus the distribution. A retail buyer took a sample of 73 stamps from the lot and sorted them by age. The results are given in the table provided. Test at the 5% level of significance whether there is sufficient evidence in the data to conclude that the age distribution of the lot is different from what was claimed by the seller. So we want to do a goodness of fit of the data from the observations to see how that matches with the probability distribution. So we'll be looking at doing a goodness of fit test to a discrete probability distribution, which is what section 2 of chapter 11 is all about. So that's where we're headed. Okay, and we're doing testing here. So we're testing the level of significance, and we're talking about level of significance. That's going to be our alpha is going to be 0.05 is what we'll be heading there for the 5% level of significance. We have a sample size of 73. So we have 73 in our sample, so that's data we're going to need as well. And then we've got this, okay, we've got a claim distribution and observed frequency. And since we're testing, that means we're testing hypotheses. And that's going to mean we're going to do that 5-step process. So first thing we need to do is determine what our null hypothesis and our alternative hypotheses are. And as was talked about, that here, because we're doing this goodness of fit, the hypotheses are in words rather than a formula like we had before. So I'll comment here that our null hypothesis is that the seller distribution is correct. In other words, the data that the buyer sampled and observed matches the claim distribution. And the alternative hypothesis is that the seller distribution, what he claimed or she claimed, what was being sold, is not correct. All right, so step 2 then, we identify the test statistic that we'll be using for our hypothesis testing. And we're in this section on testing goodness of fit for discrete probability distribution. So that's probably what we're going to be doing here, and it is. And that's going to be a chi-squared distribution, where we're summing over the observation minus the expected value squared divided by the expected value. Okay, so up here we have the claim distribution here and our observations here. So the first thing that I thought of when I saw this was this looks like a great thing to dump into Excel, because a spreadsheet should be a good way to calculate out the whole chi-squared value here for this. So let's jump over to Excel and look what I did to put this in. So you can see before you here what that data is on the before 1940 claimed observed. I essentially took that little matrix and put it into Excel. And let's jump over there. I'll click on Excel. Oh, there we are. So we're in Excel. This is that same data that we had directly from problem number 3. And I'll draw it this way. So here is our claimed values and our observed values, just that we had. They're the numbers that I had just written off to the side of the chart just previously there when I was drawing. So what we'll need to be determining here is to use our chi-distribution, chi-squared distribution, which we had that was the sum of the observed minus the expected squared divided by the expected. Now, observed value, we have the observed value. We need to determine what this expected value is. So what I did to determine the expected value is based on the total number of samples that we have if we have the total number times the probability for each different level, so our levels are before 1940, 1940 to 1959, 1960, 1979, after 1979. So if we multiply 0.1 times 73, we should be able to get this expected value. So what I did there, let's come down and look at what I did in that cell. So in that cell, I've got, click on this again, C4, the dollar sign there to keep it from changing as I copy it down. So that's the blue, and the blue matches the N93, so that's the number, times the red, C8, which is the claimed. So that gets me the 0.1 times 7.3, or we actually multiply that out, 7.3. Then I copied that down to each of the other cells and calculated all the expected values for 73 observations. So if I had 73 observations, what I would have expected is a makeup to look like this. Okay, so now I've got the O and the E. So to determine this chi-square distribution, I'm going to have to sum the O minus E squared over E. And that's what I did in this next column. O minus E squared. Doing this in pieces versus all at once. You could do it all at once. But I did it in pieces. So here, O minus E, let's go back again. So O was the blue, D8. Here, 6 in this case. And I'm going to minus the expected, O minus E, so the blue minus the red. And then that caret 2, that's going to square what's inside the parentheses. So O minus E, just like this top part, squared. Okay, so I do that for, each of the cells. So O minus E for each of the levels to get the value of what that is squared. Then I'm going to divide that by E. So I come over here. I'm going to take the value, O minus E squared, and divide it by the expected value. So up here, we've got the H8 divided by F8, so the blue divided by the red to give us the value. And that gives us each one of, for each row, the O minus E squared divided by E. Then I want to add those up, so I'm going to sum those up. So I'm going to sum across all of those. And down here I've got the word sum. So I've got the auto sum feature that's going to add those across each of the 4 levels. And that gets me the sum of the O minus E squared divided by E. So my value of my chi-square test statistic is 4.8082. Okay, let's jump back to where we were a moment ago. Chink. So our chi-square test statistic value is 4.8082. All right, step 4 in our process is determine the value to find the range that we're looking at for our critical value, the rejection region. So our x squared at alpha, that's x squared at infinity. So x squared at alpha, this is going to be not x squared, chi squared. So chi squared at 0.05. And we have to know the degrees of freedom for that. Okay, so degrees of freedom. So where do we find degrees of freedom? If we go back to our formulation there in the text where it talks about our test statistic, that it talks about our degrees of freedom is equal to I minus 1. What's this I? In this case, the I is the number of different levels, the number of different sorting categories, the slots that it could be in. So that's what we're looking at in terms of I from 1 to up to capital I. In this case is 4. So in this case, it's going to be 4 levels there minus 1. So our degrees of freedom is going to be 3. So degrees of freedom 3. We go back into the chapter 12 into appendices, essentially, to find the chi-squared distribution. So chi-squared at 0.05 for the level of significance at degrees of freedom 3. We look at that table and we see that 7.815. So our reject region is 7.815 to infinity. And as we mentioned, that the chi-square distribution, We're always looking at a right tail distribution, so this is that 7.815. So for 5, we compare that. So our value was the 4.8082, and we do not reject the alternative hypothesis. So we accept the hypothesis that the claim distribution, based on the values that were observed in that 73 stamp sample, was appropriately from the claim distribution.